If you have ever used a battery-powered device or plugged an appliance into a wall socket, you have encountered two different types of electric current: direct current, DC, and alternating current, AC. DC flows in one direction and has a constant voltage, while AC changes direction and voltage periodically. Most devices need either DC or AC to function properly, but sometimes you need to convert one into the other. How do you do that? You use a device called inverter. In this video, you will learn how they work and why they are important for many applications. Inverters are electronic circuits that can change the type of electric current. An inverter converts DC to AC. They are usually composed of ICs, diodes, transistors, or other components that can control the flow of current. Inverters can have different designs and specifications depending on the input and output voltage, frequency, power, and waveform. There are many reasons why you might need to convert DC to AC. For example, you might want to use a solar panel or a battery to power an AC device, such as a fan or a light bulb. In this case, you need an inverter to change the DC output of the solar panel or battery to AC. An inverter works by switching the DC input on and off rapidly, creating pulses of current that alternate between positive and negative. These pulses are then filtered and smoothed by capacitors and inductors to form a sinusoidal waveform, which is the most common type of AC. The frequency and amplitude of the AC output depend on the switching speed and the input voltage of the inverter. Some inverters can also produce different types of AC waveforms, such as square, triangular, or modified sine waves, depending on the application. Solar inverters convert the DC output of solar panels to AC for the grid or local loads. Uninterruptible power supplies, UPS, provide backup power in case of a power outage, using batteries or other sources of DC power and inverters to supply AC power to critical loads. Electric vehicles, EV, use electric motors and batteries to propel themselves. Inverters convert the DC power from the batteries to AC power for the motors. Simple DC to AC inverter circuit. 12 volts battery generate DC supply and inverter will change it into AC supply of 220 volts, 50 Hz to use to operate any appliances. The 12 volts DC supply from the positive terminal of the battery comes to the primary winding of transformer, which is center tapped. The two ends of the primary winding of transformer, A and B point, are connected to the two-way switch to the ground. If the switch connects to a point of the primary winding, the current flows from the battery into upper half of primary winding, O, through a contact of THE switch to the ground. If switch turned from a point into B point, this time the current number 1 stops flowing. Then, the current 2 flows to the ground through O and contact B of the switch. Here, two-way switch is controlled with the square wave oscillator. It generates a frequency of 50 Hz. It causes the switch to select between A and B point with speed about 50 times per second. Also, the current 1 and 2 flows to the transformer alternately at a rate of 50 times per second. So, the current flows into the transformer alternately look like AC voltage. We know that transformers work on the principle of electromagnetic induction. When current flow in primary winding EMF induced and a current will be induced into the secondary winding of transformer, which it causes AC voltage 220 volt 50 Hz. Now, the voltage is used to be supplied to the various types of electrical equipment that operate in 220 volt AC supply. If we have a voltage of 12 volts DC and we need 240 volts AC to run a 3000 watt kettle, we first have to do a bit of maths. To power our kettle we want 3000 watts at 240 volts, so to find the current divide the watts, power, by the voltage and we get 12.5 amps current. Now let's look at the input. We still need 3000 watts, but this time the voltage is only 12 volts. So, that's a lot of current, and that means big cables. So you can see, getting a large voltage from a small one using a transformer is easy, but getting the power is a problem. 90% of inverters on the market are built like this. They are usually between 80 and 90% efficient and usually have built-in some sort of low battery voltage protection and thermal protection. But more usually you will find that they are limited to just a few hundred watts and can only run small electrical devices. There is, however, another problem. The fact that the battery is just switched one way, then another gives a very jagged output, and some sensitive electronic equipment can be damaged by this. In order to try to mitigate this, some inverters have what is called a modified sine wave output. All these inverters do is step up and down the voltage as it is being switched. So as the switch changes, a voltage is applied, then stepped up a bit, then a bit more, then down again, and down lower, than the switch flips over and the cycle is repeated. You see, the red line is the pure sine wave, the green line is a square wave which is easy to create electronically, and the blue line is a modified square wave to make it more like a sine wave. While an inverter can produce different waveforms, a pure sine wave output is preferable because many electrical products are designed to work best with a sine wave AC power source. A high-quality and well-designed inverter ensures that the output is purely in the form of a sine wave with minimal conversion losses in the system components. This simplified circuit uses a DC source to power an AC consumer, represented by a lamp. By pairing switches, we can generate AC pulses and alternate the current direction through the lamp. If switches 2 and 3 are opened, the current will flow in the opposite direction through the lamp. And if switches 1 and 4 are opened, the current will flow in the opposite direction through the lamp. The lamp in this circuit is actually receiving an alternating current, which it experiences as a square wave. A high-quality inverter operates on a similar principle, but includes several functions to improve output quality and conversion efficiency. Switching is performed using electrical switches like FETs and IGBTs, and control pulses are generated by a control circuit. Energy storage elements such as inductors and capacitors aid in filtering and smoothing. The smoother the wave, the higher the quality of the output will be. The sine wave inverter uses a low-power electronic signal generator to produce a 60 Hz reference sine wave and a 60 Hz square wave, synchronized with the sine wave. The reference sine wave goes to the PWM circuit along with a triangular wave that is used to sample the sine wave values to produce a PWM control output. This PWM control signal operates an electronic switch that converts the DC input to a PWM voltage. The PWM voltage and the 60 Hz square wave are inputs to the H-bridge. The output of the H-bridge is an alternating PWM voltage. The filter converts the alternating PWM voltage to a utility-quality sine wave that goes to a transformer that steps it up for use by the load. A pure sine wave inverter can power most appliances that use AC power, such as refrigerators, microwaves, TVs, and lights. However, some sensitive electronics or motors require a pure sine wave inverter to function properly. These include variable speed power tools, laser printers, and certain medical equipment. Always check the manufacturer's specifications or consult a qualified electrician to determine if a pure sine wave inverter is needed for a specific appliance. No inverter is 100% efficient. At best, they come close to 92%. At worst, they can drop to 50 or 60%. An inverter needs power to operate, so expect to lose around 10 to 20 watts of power from your batteries just having the thing connected and turned on. Once it is operating, this well may increase, especially if it has to run the internal fan to keep cool. As you go up the price bracket though, some inverters have a sleep mode and will reduce their own consumption to a few milliamps until power is required. Any device that has an inductive load, something with a motor, will always be less efficient running through an inverter than plugged straight into the mains electrical supply. It's all to do with power factors where the voltage and current become slightly out of phase. When choosing an inverter, always go for a slightly higher output watts than you think you need. It is better to have a 1000 watt inverter running at 700 watts than a 700 watt inverter running flat out. As a rule, assume your inverter is only 80% efficient and work from there.